Sweet. So the first question is, if I add my quote to the quote file at the end, and I'm not the first one to be making the merge request, my merge request is guaranteed to have a conflict. True or false? Or it depends, or I don't know. All right, so when I created that question, I almost marked this one as a true answer, as a correct answer, because it is almost guaranteed that you will have a merge conflict, right? But it says is guaranteed. It's like, there is a small chance you will not have a merge conflict. When? When you will not have a merge conflict? So it depends, but what it depends on. So we have a file, we have the quotes, you're making your quote the last one, and then you're making a merge request, and you're not the last one to make the first one to make the merge request. So somebody did a change before you, right? So you will have a merge conflict almost guaranteed, but in which situation you will not have a merge conflict? So we have the quotes file. Let's say it has two quotes already in. You edit. So this is your edit quote at the end. So this is the file after the change. And then you are not the first one to make a merge request. So somebody did a change before you, right? So somebody saw these two quotes and somebody made a change such that your change is not in a conflict with that change. So what would have to happen? What would have to happen is the previous person change would have to go either here or here, right? Because if it goes at the end of the file, you will have a merge conflict, right? So when we are doing the quotes and you're adding quotes at the end of the file, you're guaranteed to have a merge conflict with the person which did that before you, right? But if somebody added a quote as a first quote and you've added a quote as a last quote, so there is a change happening here and a change happening here, they don't conflict with each other. They can be done in either order and the end result will be fine, right? But if two people added something at the end, then it depends which order I do things, because if this guy goes first and then I go next, my quote will be after him or her. Or if I do the reverse, it will be the reverse, right? So there is a conflict and we have to resolve the conflict, right? So the changes in Git which don't affect in which order I do things kind of don't generate merge conflicts and they're kind of fine. But the changes which depend on the order in which I do the operations, they usually have to be manually resolved, right? And you have to manually fix them. So Git is really good in working out that, oh yeah, all those changes can be done kind of concurrently and they don't affect each other. But in some situations, you have to merge the things yourself. So the new lines, they are not as important as the relationship of the change towards the end of file or the beginning of the file, right? Yeah, exactly. So when things are not done at the end, or if the change is not in the same place, then you will not have the conflict, right? So that's what I mean. So originally, when we set this merge request kind of a task, people keep adding things at the end, which means every single time there is a commit before the merge request is handled, there will be a conflict and you need to resolve it, right? And part of the thing is that I've made my own first merge request before anybody else, such that to force that there will be a conflict even for the first person, right? So merge request number 2 was in conflict with merge request number 1, which was mine, and that was the idea. The idea was to have conflicts, which then resulted in a bit of a mess, right? Because it's many of us, and we have a lot of merge conflicts, and we have a lot of merges to do. So anyway, coming back to this merge request task, if we go to all the merge requests, we have quite a lot of them not processed. So we are like merge request number 55. We have 41 to go. And then if we go all the way to the smallest numbers, we have merge request number 4, which is the smallest right now. And this one has been approved and it's ready to merge, and it does not seem to have merge conflict. So we agreed that either the author or the author should kind of merge it, but you know, anybody can merge things. So if you are, so I will merge this one. So we go to the next one. Okay, so now if we go to merge requests, again, and then go all the way to the smallest one. The smallest one is 6. So we go to number 6, and then we check. So it's not approved because it has conflicts. So the person, Johan, needs to now resolve the conflicts. And then once the conflicts are resolved, the person who was before that, so merge request number 5, or anybody else below can kind of approve it, right? So whoever is checking it can say, oh yeah, I can see the conflicts are resolved, I approve it, and then can immediately merge it. So we kind of clear up the pipeline, right? So we have quite a backlog. We cannot randomly clear the pipeline because we have merge conflicts, and we agreed that we're gonna process all the merge requests from the smallest numbers upwards. But you know, if you have a spare time, check yours if you're not in the current, you know, because one person will be blocking the pipeline, right? So currently the blocking pipeline is by Johan. So please, Johan, check and resolve the conflicts. When it is done, make somebody else approve you, and then once you approve, just merge it, right? Is it clear what needs to happen? It will take a while because there is always one person being the bottleneck, right? One person like blocking the pipeline. The difficulty of the thing is to get familiar with the GitLab and with merge requests, and also to get familiar with resolving the conflicts. That is actually the main point of the thing. The rest is kind of a little bit easy, but being able to resolve the conflict is a little bit tricky, right? And I encourage you to do that locally on your laptop, not to do that within the GitLab, just to do that like pull the branch, merge it, push it again, and so on. So that leaves me to one more important point. The important point is that, I mean, when you work with Git, you get kind of an intuition, like how things work, right? And everybody has their own sort of intuitions, right? So the intuitions I have not necessarily have to be the same as yours, right? But my intuitions are that there is like the Git repo, and then that's our course. And what you did, you forked it to another kind of Git repo. So you use a fork to make a copy of that repo somewhere else in your workspace, right? So now we have 2 repos. And the repos have branches. And this guy has a main branch, and you have a main branch, right? So that main branch is for this repo, and that main branch is for this repo. And then you did some changes. So most of you did some changes in the main branch here. And let's say you did some change A, right? And then you say, okay, merge request my change A to the main branch of this repo. That's how it works, right? With the merge request. And then there is a conflict, so you need to pull it back, make additional commits. So originally, let's say you had 2 commits to A, and then you added extra 2 commits, okay, for the sake of argument. So now, original merge request was like this with those 2 commits, but you added 2 extra commits. What happens? The merge request gets automatically updated, and it can see your new commits to that branch, which is your main branch, which is in the merge request, right? So what happens, some of you started working on task 1 and making commits to main which affect now the merge request which you did for task 0 because it is the same branch, which is a bad idea, right? So what should happen is you should not make changes A on main. You should have two branches, maybe a feature or something, right? Make changes in this branch and make the merge request against this branch only, right? Because then the commits to this branch will be reflected in the merge request updates, right? Does that make sense? Who says it makes sense? And who is like, I'm not sure what you're talking about. Okay, so those people who are not sure what I'm talking about, do you understand the concept of a branch in a repository? Yes, no? All right. So if we have a repo, it has a certain state. So I will kind of show it on a file. So it has like a repository has branches, and the main branch, the default branch that we work with, is called main. It used to be called master, but it turned out to be politically incorrect word. It's so funny. So now, like, we use it. We use main. Okay. Some systems still use master, and when by default, when you start something, sometimes it says, "Oh yeah, by the way, you have a master branch. Maybe you should rename it to main." Anyway, we have a branch called main, and then in this branch we have a version of a file or kind of a set of files and directories, and we kind of working with that copy. So it's sort of like a snapshot of what we have, right? And then we keep track of the changes by doing commits. So we kind of keep track of what has happened. So let's say the file was originally empty. So that would be kind of a change set 0. And then when I sort of make some changes, so I kind of say hello inside the file, then I apply that change, and then that change set is applied, and then I have a new version. We don't really have it chronologically like 0, 1, 2, and so on. We use the hash instead. So the original version had a certain hash, and then the change set had a certain hash, and then after applying my change set to the original version, I have a new hash, right? So we kind of have a certain hashes, which we identify like EF, E something, right? Which we identify the version of the file. So then you have your kind of snapshot of what you're working on in the main branch, and multiple people can work on it. And then what you can do is you can say, okay, I want to duplicate this into a new branch. So I have my development branch or my feature A branch, and I am kind of working on the same stuff, but in a different branch. Or if I'm working on a particular feature, I kind of work on that file here inside the feature branch. And creating branches and switching to branches is very simple. You just say git branch, and then you create a new branch, and then you can say git checkout, and then you make a branch name, and then you go into that particular branch. And you can jump from being in this branch to this branch to this branch, back to this one, and keep kind of seeing different versions of your file, and then switching between the different branches that you work on, right? And this is very useful because it allows us to contain the work that we're currently doing to a small place, and then keep working on multiple things at the same time without affecting each other work, right? So I can work on feature A, and I can work on feature B and feature C, and they don't affect one another. And then when I'm done with feature A, I can kind of merge it with my development or main branch and then show it to other people, right? And before I do that, I usually do my merge request, right? So I say, look, I have this feature A, I want it to be merged into main. please review it and tell me if it's okay. And then we run the pipeline, we run the review, and then if it's approved, we merge it. And then this branch discontinues, and then this branch becomes the main branch. Sometimes it is visualized like a tree. So we have sort of like a root. We have the main branch, we have the commit, and then after this commit, we have like a split. So part of the development continues with the main branch, but part goes, let's say, to the feature A, okay? And then I have a first commit in my feature A branch. And then I have another commit and another commit. And then at some point, I'm saying, look, I would like to merge it. So I'm making merge request. And then this branch may continue, or it may discontinue. And then I'm doing a merge request, and the merge request is being merged into the main branch via a commit. And there are different ways. We either merge it with all those commits as individual commits, or we kind of combine it into a single commit, right? So we often see this visualization as I have multiple branches, and they either branch off main, or they can branch off your branches. So I can have another branch, which is like a bug A, which is a bug on my feature, and then I kind of forked it, like from this commit, I have kind of new commits fixing a bug, and then I'm merging it back to my own branch. So you can do arbitrary things, right? You can kind of arbitrarily complicate your branching strategy and your merging strategy the way you want. Typically, we usually have a main which is protected, which does not allow people to commit directly, only through merges. And then we have development branch, which usually allows developers to commit directly. And then we have some feature or bug branches to work on individual items, right? So when you fork your original repo, what you should do is you should say, okay, I'm working on task 0. You should branch, say, oh, I want task 0 branch. And you should be working on task 0 branch. And then from task 0 branch, you should make a merge request, right? That would be kind of a tidy way of dealing with it. And then when you start working on task 1, you should say, okay, now I'm working on task 1. I create task 1 branch, and I'm kind of working on it, right? And then you can split it even more. You can say, okay, task 1 is more complicated. I will do hello world kind of separate, and I will do the paper scissors separate. So I have another 2 branches and so on, right? Is it helpful? Does it kind of explain a little bit better what should happen? All right, so let's go back to the quiz. And I have a question too, which I probably spoiled already. So let's try it. So the question 2 was, forking a project and pushing all commits to the main branch is a good idea. True, false, I don't know, or it depends. So if you forked it and you start pushing everything to main, is it a good idea? Well, you know, it's not. So it's not a good idea. And it really does not depend on anything. Even if you're alone, and even if it's a very tiny project, yeah, probably should not be doing that, right? So I don't think it depends, but you should always use branches. And even if you don't think you're using branches, you are using branches because you're using a main branch, right? You are using branches. All right, so there are kind of why it is not a good idea. First of all, it creates kind of confusion, and it creates problems, as I explained here, with task 0 and task 1, right? So now people have still some merge requests hanging for task 0 for the quote, and it gets polluted with commits related to task 1, which is about Solidity, right? And those two things have nothing in common. They should not be polluting. So if I'm committing something about my Solidity, it should not affect my quote merge request at all, right? Those are two separate things. And that demonstrates that it leads to kind of chaos. Like if you're working with a team, even if it's only 3 or 4 of you, and one guy kind of pushes something which is completely not related to the merge request into the commits. It's like, whoa, wait a minute. What is happening here, right? We're fixing a bug, and now you kind of updating the documentation. Like it's not the same thing, right? It should be separate. So it should be isolated to its own branch. Yeah, exactly. It's kind of hard to go back to what was the working version. It's really hard to make resolve conflicts because you get all these extra polluting things and you don't know like how to deal with it. I have a student and we have like, it's only two of us. So we have a very simple kind of workflow. But what happens is he makes a merge request. He checks like I check if his changes are kind of okay. And then we have to make sure that the pipeline works, right? And what happens sometimes, I don't have time immediately to check his stuff. So what he does, he makes changes, like he makes new feature, he makes a merge request for that feature, and immediately he starts new branch and he starts working on a new branch for new feature, right? And he makes a new merge request. So we have feature A merge request, and then we feature B merge requests, like we have with quotes, right? And then what happens is he finished feature A, it's all done, it's all tested, but the pipeline doesn't go. Like he forgot some linter error or something. Like he missed something in feature A that makes the pipeline not work, right? And then I kind of come to the approval, and he says in the comments, yeah, that thing about the pipeline is fixed in feature B. So he did not fix it here because he started already working on the new branch and new things, and he already fixed it. So there is no point backporting it here. Like if we were in a bigger team, we probably would be much more strict, and we would say, okay, now you have to cherry pick changes from branch B, backport them to branch A, and kind of apply them here. But because it's only two of us, and because we kind of simplify things, and he says, yeah, it's already been fixed, I kind of conditionally approve it, we merge it, and then we go to feature B, and then the pipeline is fine, right? Everything works. So we sort of make kind of a simplified version of the workflow, but he still contains every single feature into its own branch, and we kind of do that, branch by branch. And then if there is a bug, we kind of isolate it as well into an individual branch. So it's harder to go back to previous stable versions. It's harder to manage the complexity of the project. It's harder to pinpoint what is wrong where, like why for example, why pipeline does not work, and so on. So it's a good idea to use branches. Can it get complicated? Initially, yes. Especially if you're starting working with branches, you get a little bit overwhelmed. Like it's all this, like there is this main project upstream, there is your project, you have one laptop and your friend has a laptop, and maybe you have a PC, and you end up with multiple copies of things, and you get kind of confused, like what is where and how things work, right? But the more time you spend with Git, and the more you sort of understand how this decentralized version control kind of works, the more familiar you become, and then branching becomes non-issue. Like it's like so normal to have just branches, right? And Git helps you, like it shows you all the list of the branches, and if you follow like a naming convention, it's kind of easy to navigate. So just try it out. Like there is no real failure with the quotes or with GitLab, so you can kind of try out and if you get stuck or if you don't know how to do something, then ask TAs or ask me, right? All right, so that's about the Git. Work as much as you can with Git. Make sure that when you're forking stuff, you fork it to the proper workspace. I talked about it before through Issue Tracker, that some people forked advanced programming into the cloud workspace. Yeah, you should not do that, right? Then Christopher asks me like, oh yeah, where, somebody submits the project, but it's in your course, right? It's like, yeah, I know, students do that. So we kind of see each other work. It's not the end of the world, but try not to do that. Try kind of fork things to the proper place. So use proper workspaces, and then inside your workspace, you are free to do whatever you want. You can fork multiple times and you can create multiple subgroups and so on. You're kind of like, you have almost super user privileges for your own, managing your own workspace and managing your own projects and your subgroups. And you can kind of organize it the way you want. You can organize it per task. You can organize it per certain activity, whatever you like, right? You can create as many projects and as many forks as you wish. So you can create forks, delete forks, you know, mess up things, clean things, and so on. So it's up to you. So whatever you do in your workspace, it's entirely up to you. And you have quite a lot of power to do whatever you want, right? So then once you create it, kind of make sure that you're working in branches for particular things, right? So task 0, okay, branch task 0, for example. Always use branches, and then try to be quick in managing the merge conflicts when it comes to you, right? All right. Any questions about Git and what needs to be done for the quotes? So you need to wait for your time for your merge request to be the smallest number. Then you need to resolve the conflicts and merge it. Like before you can merge it, you have to ask somebody for the approval, right? It's a very good idea, and we are doing it, that you cannot approve yourself. You need another person to approve your code, right? And you should do this practice in your group work and in your kind of Git flow in general, that you set this rule that if there is a merge request, the merge request author cannot approve it. It has to be approved by somebody else, like a additional person. Why is that? There are two main reasons for this. The first reason is that another person, another developer can see your code and can have feedback and give you kind of a comments with the fresh look, right? When we work with our own code, we almost always become a bit blind to some of the things, and we don't see obvious things. And somebody else looking at it can kind of immediately do that, right? So like when the student shows me his kind of merge requests, I immediately say, yeah, why using this constant here without declaring it? It's like, oh yeah, I forgot, right? So he kind of cleans up the code. Or I can ask him like, why you have this kind of a very nested if statement here, right? So anyway, it's a very good idea for a second person to just check what you've done to kind of improve it. And then if you're working with the team, if the second person checks your code, there is another person who kind of knows what you were working on and knows what you did. So if you get sick, or if somebody asks, oh, who did this? Then there is another person who knows what's going on, right? So it become less silo and more kind of a team based. So those two reasons are very good for pair programming, but they're also very good for making sure that somebody approves your work. And then we often have a definition of done. Like, what does that mean that the piece of work is done, right? And it kind of depends how strict you want to be with your team, but you kind of need to consider. So from like checkboxes, right? So the code is there, right? So let's say we need a feature and somebody said, yeah, I've done the feature, right? But does that work? Have you tested it? So the code is there, okay, tick, but does it work? Okay. Does it have tests? Is it documented? And so on, right? So you can have multiple things, and then it's like, oh yeah, it has. Okay, it's considered done, right? So you have to specify, what does it mean that we agree that something is done, right? Usually it means the code is there, it works, it's documented, and it's kind of tidied, right? It's like checked by the linter, and there is no obvious problems, right? The linter does not complain, right? So some of those checks can be automated as part of the pipeline, and some of it is kind of us doing things manually, right? Okay, so any questions about this or Git? If not, how are we doing with time? Okay, not so great. So Solidity. Um, I don't know exactly what the teacher taught you, so we will have to go through a little bit of a repeat, and then we will do some practical things, right? So what we are learning is we're learning a new programming language, which has some interesting features, and we will do some exercises with it. So we need to get a little bit of our heads around the Solidity as a language and the EVM as a kind of virtual machine. Um, but to do this, we need some fundamental concepts about blockchains. And I think she did kind of good job covering that. But I will sort of, run some obvious things with you again. So one of the questions is ETH and ETC the same currency? So what does ETH and ETC stand for? Who knows? So ETH stands for Ether. It's the fundamental unit in the Ethereum blockchain. So Ether. And then ETH stands for Ether Foundation. It's the foundation group which manages the network. And then there was a fork historically, which is called Ethereum Classic. Classic with C. And these guys were more religious about non-changing of the blockchain. So what happened was the Ethereum Foundation had a bug, and that led to some of investors losing money. And they sort of, so there was a blockchain, there was this bug, some investors lost money, and they kind of said, okay, we have to go back, change it, and kind of fork it, hard fork it. So now we had two Ethereums. And those two Ethereums is Ethereum Classic, which did not do the change, and Ethereum Foundation, which did the change, right? So Ethereum Classic is not very popular anymore. It's not as economically viable, but they still use proof of work, and they kind of maintain this non-changing, immutable kind of properties of blockchain, right? So it's kind of an interesting use case of a system which is supposed to be immutable, but because of legal and kind of operational circumstances, kind of became muted, right? Changed. Um, so when we say blockchains are immutable, we say, yeah, but it depends a little bit, right? So we have an example where a blockchain became kind of changed because of the decision which was made by the community. So, all right. So then another question. Ether has a limited supply capped at around 21 million units. That is false. Ethereum does not have a cap. The supply and the burning of the currency happens all the time. So the new rewards or new kind of coins are being minted by the validators by proof of stake at the moment, by proof of work before. But the smart contracts and the computation which is happening on Ethereum is burning some um, of those resources. So there is kind of like a circular economy. So some of the coins get injected into the circulation and then get burned. and some are being minted and some are being used as a reward for the validators. So there is no actual limit, but it tries to kind of keep the circulation in check in such a way that if the system kind of grows and more users are using it, there is more ether in circulation. And if the system shrinks, there is less, right? And we kind of do that with central banks and with the normal economies as well. So when there is like problems, the central bank issues the incentives for people either locking the money and keeping them or kind of spending them. So either by locking there is less money in circulation, or by spending there is more money in circulation, right? Okay, so which currency has 21 million and it's capped?
Bitcoin.
Yes. So Bitcoin is one of those currencies that has the kind of upper limit, and there will be never more than around 21 million coins in circulation. In fact, because some people make mistakes and some people lose their wallets and so on and so forth, there is a tendency to be less and less in actual circulation, right? Because once you burn the money by sending them to a wrong address or by losing your private keys, then that's unrecoverable. All right. Okay, we have another quiz. So there are many diverse networks that use EVM. Yeah, that is kind of an obvious. And when we talked about ETH and ETC, there is already two networks, right? So it has to be true. So it's true. There are many different networks, and there are quite diverse. Not all networks use EVM, but there are many that do use EVM. The most prominent is probably Binance Chain, which is another EVM compatible network. And there is a lot of networks which are built on top of the base networks. So we have overlay networks, so-called second layer networks, and they are very popular for Ethereum and for EVM. The important thing to remember is that each network, it's like it is its own system, right? So if I have Ethereum coins in Ethereum network, then maybe there is an Ethereum coin in Binance, but those Ether in Binance and my Ether in Ethereum are kind of different Ether. Even though they might be one-to-one in value, those are kind of different coins. And we have to kind of be careful like how we using the funds, because you cannot really do you cannot send coins from one network to another without going through a bridge. You cannot directly from your wallet say, I want to send money from my Ethereum mainnet to my testnet and from my testnet back to my mainnet and things like that, right? That does not work, but it is sometimes possible to misuse or mishandle addresses and kind of make a mistake, right? And that can lead to lost funds. There will never be creation of funds like spontaneously, but there is definitely possibility of losing funds if you do something between the networks which not supposed to work. So IPFS is another peer-to-peer network which is used for storage. They now have like a Filecoin, a kind of a native currency for that as well, but peer-to-peer networks don't have to have a currency. They can just work without having some sort of currency. But most cryptocurrencies, they have some sort of a value system attached to it, and they have kind of a built-in native currency. Binance Chain is actually a verbatim copy of Ethereum, just owned by Binance. And then there are many peer-to-peer networks or overlay networks that have nothing to do with EVM. So Bitcoin is one example, and it's not EVM based and it's not compatible with EVM. But there is a lot of second layer networks which adapted EVM and Solidity, so you can use your smart contracts on those networks. We're actually doing research on some of the decentralized exchanges which redeployed a particular solution on multiple networks. So we have like an example of a particular system that has been redeployed 27 times on 27 different networks, right? And then it's kind of interesting how you coordinate, how you manage the complexity of maintaining and updating kind of such diverse deployments. So we have a PhD student kind of working on best practices on how you deal with this kind of type of software deployments. All right, so Solidity. It's a high-level language designed for writing smart contracts which run on the Ethereum virtual machine. But as I said, the Ethereum part does not mean it has to be on the Ethereum network. It can be on any network, which just adapted EVM technology for the smart contracts. So what are smart contracts? It's kind of a little bit interesting because some people say they are not smart and they are not really contracts, which is true. They're not smart and they are not contracts, but it is kind of like automating something that usually requires a third party, but it's automated to a point where there is no need for a third party, right? So one example of a smart contract is a vending machine where you basically can buy a drink without a seller being inside the vending machine, right? So the vending machine tells you, okay, if you give me such and such amount of coins and you make a certain selection, I will give you a drink, right? And then it's sort of an automated agreement between you and something which is inanimate to fulfill that, right? And it almost always works, right? It almost always works unless the coins get jammed or the power get cut in the wrong time and something like that, right? So the vending machine in general is considered kind of like a replacement for a third-party interaction. And then it sort of works. So it's the same here. It's like an environment where you can create those type of vending machines. So you can create certain things which will always happen certain way, and they don't require any human interaction. Like they kind of just happen the way you programmed it, right? It has a nice properties. It has properties that it's autonomous, so it does not belong to anybody, and it has a property that it cannot be shut down. So if you set up this type of vending machine or like rock, paper, scissors on the blockchain, it is something that nobody can like actually turn off. It's even you yourself, like it's there forever. So there are certain kind of properties that make it useful for certain types of activities and kind of useless for other types of activities. And then people get really confused. What is it good for and what is it bad for, right? And the jury is still out. There is like a lot of experiments going out. But there are some innovations and some things that point that some of the use cases are kind of better than what we have as alternatives. They offer anonymity, they offer verifiability, and they offer systems that are collusion free, that humans cannot kind of collude and kind of rig the game, right? So there are certain aspects that make it kind of suitable for certain type of activities, including financial activities. Okay, so let's do maybe two more slides and then we'll have a break. So this one is an easy question, just if you are paying attention. Did you got Solidity examples in the lectures before? Yeah. So Solidity is a little similar to JavaScript. Yes, it is. They sort of use the JavaScript syntax to make Solidity in the first place, so it is similar. Okay, one more. Solidity is dynamically typed. No, it's not. It's statically typed language. Okay. JavaScript is dynamically typed. Who thinks JavaScript is dynamically typed? Okay, it is. Okay, one more. So what keyword do we use to declare an unsigned integer in Solidity? It's easy. We use uint. Correct. Most people got it right. Perfect. So now one more. What is uint equivalent to? It's basically an alias to one of the other types. I know, I know. Why would the 256 be the default? Yeah, but it is, right? It's the largest. So the largest integer in Solidity is 256 bits, and uint basically goes to the largest. Why do you think it's that? Why do you think they made that choice to make uint go with uint 256 instead of like 64 or 32? So first of all, there is no real hardware link of Solidity to real hardware or 64 bits or 32-bit hardware, right? So the link is kind of very abstract. Um, and second of all, Solidity was designed to be a language for smart contracts, and smart contracts have to deal with value. And then if you're dealing with value, you want to minimize the overflow or underflow on your arithmetic operations. So if you make the default the largest possible kind of int that you can represent, then you will sort of cover most of the cases, right? Of course, you always have edge cases if your number goes above or under the limits, but 256 is the largest possible number representable in the language. So then they went with this. Obviously, it's inefficient, so you probably should never use uint. You should probably always use the size that you need for your representation of what you want to represent. But they kind of went with the default pointing to this one. Okay, so let's have a break, and then I will talk a little bit about the basic types of in Solidity, and then we will kind of dive a little bit more into the syntax and into the details of the language. And oh, sorry, yeah. So and then you can emit that event, and that event gets recorded in the transaction log of the blockchain. So it's like permanent, but it's kind of easy to get notified about this. So those are kind of two nice things. And then we have to have gas. And gas is to prevent abuse. And the EVM needs to kind of charge for computing and for storage. It's kind of like Amazon or any cloud service, right? Any cloud service, you can do some computations and you can do some storing of stuff in there, and then usually you have to pay. What are the typical abuses that could happen if we did not have concept of gas? What do you think? Name some. So we need gas. Why? Why we need gas? It kind of says it on the slide abstractly, but concretely, yeah? Exactly. Infinite loops. Oh. Right. So infinite, we can say in quotes, is just to prevent very, very long loops, right? But infinite as well. Like we don't want loops forever, right? We don't want something that kind of crunches something forever. Okay, so that's definitely the case. And then we don't want infinite recursions neither, right? So we don't want a function to call itself forever. And then we don't want a function which calls itself forever and stores something, right? In a list, which kind of expands the storage forever, right? So like infinite storage, right? So we kind of to prevent that. Yeah, did you do like a fork bump in the operating systems course, where you fork a process kind of like in a loop, kind of forever, to kill the system? Yeah. All right, so about gas, read-write to storage is expensive, and we try not to use it if we can avoid it. Smaller data units like UINT 8 or 16 should be used instead of UINT or UINT 256 if you don't need that. So if you're storing values between, 1 and 8, yeah, maybe you should go with the smallest possible storage unit instead of 256, right? Loops can also be expensive, so you try to avoid using loops. And external calls are expensive, so you try to avoid them as well. So when you're programming, you sort of normally you do programming for the purpose of maintenance and kind of a conciseness and so on. Here, you have to kind of be doing it mostly for the economical effects. So you're trying to avoid things that cost money and try to use things that are cheaper. And it kind of leads to very interesting phenomenon. One of those phenomenon is that we have this type called address, right? And you would think the address is the cost of storing or using an address is constant because it is like 256 bits kind of hash, right? And that would be almost true, but because EVM makes optimizations, if you have a hash, so this is like 256 bits hash, right? So I don't know, like A, B, C, D, 19, blah, 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 right? It's kind of a long hash, right? And it has 256, right? But we don't represent it as a fixed size data structure if we have a hash which has a lot of zero upfront and then says A, B, C, D, blah, blah, blah. Those zeros don't have to be stored because those are zeros. So we don't store them and we can use that space for storing another hash. So hashes which have a lot of zeros up front are cheaper than the hashes which don't. So what people do, they kind of try to guess certain hashes that have a lot of zeros up front and use them because they are valuable because they cost less money to do smart contracts with, right? And there is kind of an economy of doing hashes with a lot of zeros up front. Okay, so then we have memory versus storage. Storage is everything that is stored in the blockchain. So it's all the state that is stored in the blockchain itself. And memory is transient. It's something that we store while we're computing functions or some behaviors of the smart contract, right? So storage variables exist like permanently. It's kind of like a persistent storage. And memory is like a volatile storage that we use for variables that are just living during our computation. And then when we finish computing, they disappear, right? They are garbage collected. So it's kind of similar to thinking about memory and disk, right? So of course, memory is much cheaper, but it's volatile, whereas storage gives you persistence, but it's kind of more expensive. And then there is one more, which is call data and memory. So call data is all this read-only stuff that the function gets as a function parameters. And then it can also be read-only stuff that is passed to the function. And memory is more read-write and can persist across invocations, right? So again, memory is more expensive, but it gives you more flexibility. And call data is much cheaper because it's read-only. It does not need to be copied from place to place, but it's a little bit limited to what you can do with it, right? But if you're passing like a big array, and the array is kind of read in your function, you can declare your array as call data, and then it will be passed by reference to the memory location, which is read only, and will not be kind of made copies of, and it will be cheaper in case of gas usage, right? Is that kind of clear? Conceptually, I think it's quite straightforward. So let's dig into it a little bit. Which function type allows a function to read the blockchain state but not modify it? I didn't explain it yet, so it's a little bit guessing. All right, so we had pure and view, and we talked about public, external, and payable. So public externals are modifiers for the functions who can call them. Payable is modifier for making sure if the given function can carry value into the constructor or not. And then we have two modifiers, which is pure and view. And indeed, view is the one which marks a function that it will be read only from the blockchain state, but it will not modify it, right? So view means we are reading a state, but we're not updating it, we're not modifying it. And what pure means? Pure functions? What a pure function is? So if I have a class, let's say I have a class A, and I have a function A, which, and I have some state, let's say state A. So then if I do something here with this state, so I say A equals A plus 1, that function would be neither view nor pure. It's modifying my state, right? So that is like a normal function. If I have a function which says, okay, return return A, it would be view, right? It's only looking at the state, but not modifying anything. So it's a view. And then what would be pure if I did what? So if I say return underscore A plus 1, okay? So for a given argument, the function returns me always the same value. Like for the given argument, it returns me the argument plus 1. It's independent of the state. The state is not used here, and it's independent of anything else apart from what I'm passing, right? So a pure function calculates something based on the parameters and does not have any if statements or anything which depend on the state. It always gives the same thing. So if I pass it 10, I get 11. If I pass it 11, I get 12. And there is no exception to that. It always produces the same output for a given input, right? So it's kind of interesting because Solidity offers us to use pure and view functions, and some languages are becoming more they take the benefits of pure functions by allowing you to declare functions as pure. Even C++. in C++, you can also declare functions as pure. And what does that mean? It means that the compiler and the optimization techniques can take that as an indicator of what can happen with the functions, right? Pure functions have a beautiful property. And the beautiful property is that if I called FA, in my case, FA, to some arguments, let's say I have called it for numbers between 0 and 100, okay? So if I call this function with all those numbers once, I don't need to call this function with any of those numbers ever again, because I know exactly what is the result. The result is independent of me doing it ever, like, multiple times or out of order or whatever. It's always the same result. So I can cache it. So the runtime system, if the pure function is called once, needs to compute it for the given arguments, and then it can, we have a term which is called not caching, actually, it's called memoization. Memoization is when we remember what the state of the computation was, and we can reuse it again if we are called again, but we don't need to do the computing. We can just remember what the result was because we've done the computing once, and we only need to do the computing once. So that's the beauty of pure functions. And as I said, many languages are kind of taking advantage of it and asking programmers, tell us which of your functions are pure, because then we can do kind of various techniques for optimizing it. Okay, we have another quiz. So what will happen if a non-payable function receives ether? Transaction will succeed and contract will get ether. Transaction will revert. Transaction will succeed, but ether will be lost. Or transaction will succeed and ether will go back to the sender. So it's an error. That's an error situation, and the transaction will revert. It will say, I'm not doing anything. I'm burning the gas. I'm giving the money back to the caller, and I'm not changing any state. And we're reverting back. It's sort of like a transaction in the database. So it's atomic. If it failed, it kind of rolls back all the changes and it pretends nothing happened, right? All right, another quiz question. Only functions marked payable can accept ether. True. They make it more strict, and they kind of make Solidity more strict in terms of payments and passing value, such that less bugs can happen. And you do need to mark your functions. Okay, so write a function that sets a state of an int number and accepts a payment. So let's do that together. So it's kind of straightforward. So contracts are kind of like classes. So we would normally say contract, name it, maybe we call it num. And then we will have a function. And the function is, the task does not say to what the name it should be. So let's call it set num. And then it has to pass an uint. So n. And following, there is a space here. And following that space, we have to make the function public. So we can call it from outside. And we have to make it payable. Right? And then in the body of the function, we would say, in the contract, we would have some uint number, which is our state. And then he would say number equals underscore n. Right? So this is the declaration of the function. This is the definition. So this num is assigned with this n, and then we marked it public and payable. So quite kind of intuitive and quite straightforward, right? So then there is two more questions. To prevent infinite loops and allocate computational resources fairly, we use Ether, gas, wave, EVM. What do we use? We use gas. Yeah, we talked about it. Very nice. So then we have which operation typically consumes most gas? So emitting events, writing to storage, adding and multiplying numbers, calling view functions, or calling pure functions. Which operations typically consume the most gas? Obviously, it depends on the complexity of the functions, right? So, but writing, so this operation kind of costs more than emitting events and costs more than arithmetic operations and calling other functions. So the storage is the most expensive aspect that we have to consider. So all that state and all the writing to state is kind of big deal. It is expensive. So normally in object-oriented programming, we kind of just, use it like freely. Here, yeah, we have to kind of consider what do we need to store, why, and how we are manipulating it, because it is the most expensive aspect. Okay, so I think we have one more quiz question related to this function. So here we defined it twice. We have function A, which sets the number and it's not payable. And we have function B, which sets the number but accepts payments. We can pass money into our contract using the version B of the function, right? The version A of the function will not accept payments. So now the question is, which one uses less gas? The A public or B public payable? Which one do you think will use less gas? They have the same body, exactly the same function. One is with payable, one is without. Yes, so people think, oh yeah, the one which don't accept payments should be cheaper, right? Why? It has to have all the if statements and checks if somebody is not by mistake making payments and raising errors and like dealing with this shit, right? The other one is very simple. It like accepts the payments and does not do any checks, does not need any extra logic. So it's actually cheaper. So the surprisingly, maybe to some of the people, this version is cheaper than this one because this one has some extra generated logic to prevent payments, whereas this one does not need that extra logic. All right, so we've learned some things, I hope, and some people did quite well. And we had two people climbing because of the last question a little bit. Yeah, congrats to Tom. All right, so question, why some questions have I don't know or it depends options? Any ideas? What was it? Was it important in the quizzes? It was not that important, but it's important in the exam. So in the exam, if you have a true and false question, so let's pick some true and false question. No, this one is not that great. Yeah, for example, this one. So only functions marked payable can accept ether. Okay, we have true and false. And then normally in the exam, you will not have that it depends, and you will not have I don't know. But if you don't know, you can have don't answer, right? So you can actually not pick true or false at all, right? And then if you do pick, if you guess, in the exam, chances are there will be kind of a penalty for choosing a wrong answer, right? So in the exam, if you have true, false, so true, let's say correct answer will be 1 point, not answering at all will be 0, and answering wrongly will be -1, right? So it's not for all the questions, and I will explain in the exam, but normally if you don't know something and you have to toss a coin, usually it's better not to toss the coin at all, just to not answer. If you're tossing a coin, you are risking either a reward or a penalty, right? If you're opting out, you get 0, right? So on average, if you're always tossing a coin, you get sometimes 1, sometimes -1, so you on average should get 0, but you can kind of zero yourself by opting out and not answering, right? So that's what I don't know means. That if you don't know something in the exam, usually it's actually better not to answer than guess. And then it depends. It happens, and also it depends on your creativity, that you can interpret the question in a specific way, in which specific way the correct answer is like specific, right? And you can explain that. You can say, I consider that question with this interpretation, and in my interpretation, the answer is A or B or whatever, right? And then we grant you the benefit, and then we will grade you according to the interpretations that you suggested, right? We try to avoid that. We try to make questions so unambiguous that there is only one interpretation, but it's unavoidable that some questions are not like that. And also, some of you are so creative that even if for like 99% of the class, the question is unambiguous and it's like one interpretation, the person finds like an interpretation which is like for them easier to answer the question, and they use it. And then we give you points for that, right? So there is always like in the exam, like a special rubric saying, I like comments to the questions, and you say in question 13, I interpreted it like that, and therefore there is no correct answer at all in my interpretation. And then you will get points because you didn't answer and you explained why you didn't answer, right? Or you may say there are 2 correct answers or something. And of course, sometimes we have mistakes. So sometimes there is an error and people catch it and they explain, and then we either remove the question from the exam set or we kind of give you points. So that's how it works. And I think it works in Christopher exam similar. He also have like a section where he asks you for interpretations, and then he kind of gives you the stuff. It used to be that you call the examiner and ask the exam you tell the person that this question is ambiguous. Can we talk to the person who designed the question and blah, blah, blah. But we kind of deal with it a little bit on per case basis. So you can use the text field to kind of explain it. All right, so that's me talking a little bit about the future, which is the exam and why we have, I don't know, and it depends. Yep. Okay, so then what we will do is we are having a break now. And after the break, we will talk what we're gonna do with Solidity, and I will kind of make you do some things. So we kind of will install some software, and we'll do some simple coding, and we'll do some kind of a hands-on stuff. So I will not record that part, but I will be available in Zoom
and I will tell the Zoom people what we are doing, and then you can do it at home, okay? So let's have a break. Let's have a 10 minutes break, and then after that, we do a little bit of a preparatory work for the lab with the Solidity, okay?